excited to kick off this session on future computing models. I'll dive straight into the presentations. As with the other sessions, we'd appreciate it if, as you listen to the speakers, if you could jot down any questions you have and then be ready to ask them during the public question session. So with that, I'll dive into our work. One of the results that we've achieved is very surprising at first. And I'll try to contextualize it by doing a comparison. So the comparison is between the memory bandwidth of today's $500 graphics processor and the bisection bandwidth of a 20,000 node first generation compute cluster. The A is slightly bigger. So this is very important for the kinds of data processing that are important for business, which are typically sparse calculations. And this fact has been underappreciated. We took that idea and built a system. It's called BidMark. It's a machine learning system for general machine learning. Currently also includes deep learning. But it actually outperforms clusters in almost all cases at scale of around 100 nodes, and in a few cases, even larger clusters. And we're trying to now extend that performance and work with even larger clusters in order to multiply those gains and also to build bigger models. And there's some interesting new challenges that follow from that. So some applications of this work to the usual suspects for big data. So business intelligence, e-marketing, healthcare and health management, big and small science, and also defense applications. But there's also an interesting new space. In fact, Jeff covered a lot of these emerging applications in the last talk, which arise from the fact that you can do inference when you have full hardware leverage, which we're striving for. You can actually also do inference on mobile devices. So we built a system that fully taps the parallel hardware, graphics hardware on large machines. We're also porting it to small machines and Android so that we will have maximal computing capability on mobile devices as well. And that opens up this interesting market of user control of devices and even peer services, peer recognition of at sports events and so on. So a fascinating new business space. All right, and the work, perhaps the advantages we've had in our work are that we were able to actually draw from several different disciplines at the same time and push a bit deeper into the statistics, the hardware, co-design, and also using a bit more domain knowledge. So we build a solution that's a little bit less general but covers perhaps 90% of the application space for deep learning, for general machine learning. And we're interested in these new business models which go beyond, perhaps traditional data-centric cloud models towards distributed and peer services where users maintain more control and agency over the data.
In the field of quantum computing, we know that universal quantum computers, at least, are better for some tasks than classical computers, and I think Matthias will talk about this. But these computers are basically a long ways away. So these days, efforts are being made to construct limited capabilities computers, but at least they can reach large scales with current day technology. And one such example is analog quantum annealing optimizers, and the idea behind, and their sole task is to solve combinatorial optimization problems. So they are not universal in that sense. And the idea behind those devices is that they use something analogous to thermal annealing, where you in thermal annealing, you cool down the system for it to reach its most stable ground state, which is what we do in optimization, of course. But here we're using quantum fluctuations instead of thermal fluctuations. And this allows us access to a unique property of quantum mechanics, which is called tunneling, which allows basically the system, I don't know if you can see it there, to tunnel through energy barriers or to let the system be in configurations that are not allowed classically. So we're hoping that the hope is that these devices will considerably be faster than classical computers. However, so the exciting part of it all is that we already have 1,000 qubit working commercially available devices. But the caveat is that unlike universal quantum computing, we don't have actually we haven't provably shown that indeed quantum annealers or these quantum optimizers are indeed better, although we have benchmarks to show that they're sort of running neck to neck with state-of-the-art classical technologies. So if this indeed works at the end of the day, then I would call this technology a potentially disruptive technology, because if you could solve with a quantum annealer combinatorial optimization problems considerably faster, then of course the applications are huge. They appear everywhere. I guess every one of you have reached at some point a hard optimization problem that they could not solve. So we have diverse fields such as verification and validation, planning and scheduling, machine learning, graph theoretical problems. And so even though the usefulness of this technology is still in question, still certain branches of the government and academia and industry are considering it a risk worth taking.
Thank you. And I will not tell you now in 5 hours how a quantum computer works, but I want to tell you what we want to use it for. And while we don't know yet what the powers of an log one will be, we know that once we move to digital, the powers will be truly disruptive, and they will allow us to do things that we simply cannot do classically. They will give us personally a secure and unbreakable cryptography, totally dwarfing the threat to RSA encryption that's posed by quantum computers. But more importantly, quantum algorithms will speed up sampling problems, searching, machine learning problems, and they will totally change the way we do the material science by exponentially accelerating the simulation of quantum materials. We can use them, for example, to design novel catalysts, such as to efficiently produce fertilizer or to capture waste carbon. They will guide us towards new materials, for example, hopefully a room temperature superconductor.
So I'm going to talk about completely the other spectrum, and that is about computing in the space of SoC, system on a chip, for the very small devices like wearables and medical devices, and basically everything that today we have, which is the next wave of smartphone getting into IoT, or what Jeff actually called it, cognitive IoT. Now, the challenge in this space is that the communication and computing, to bring it down to the level of very low power, is very complex. At the same time, the market is so fragmented that you cannot justify to build a specific SoC for a given segment. For example, in the mobile space, the market was so big that one could build specific SoCs for these mobile segments. But for the wearables, because the applications are very different, the environments are very different, it's not so possible to build so many SoCs. So one of the interesting models is that to build programmable SoCs. That means that you have the CPU and communications and all of these things in hardware being assisted by some sort of the programmer capability and being designed as a one architecture factor, but being developed across different multiplicity of applications that applies to the IoT market. Now, if you look at these things, there are actually several challenges. So how you separate the communications and computing powers between the design of the hardware. How you bring, for example, hardware assist using programmable FPGA. Again, this has been done before for the large-scale computing, but not in the low-power devices that will have very low costs in the low power space. How you bring packaging and integrations, for example. How you make it dynamically adaptable to the applications you run. For example, if you're doing a wearable device like a Fitbit, you want to actually adapt the programming to human activity configurations and optimize it for that. But if you're using it for example, industrial lighting, again, these things have to be low power and has to last for a long time. How you adjust it to those algorithms and so forth. Finally, the way you manage the power between the communication and computing in the device and between the hardware and software is a big challenge. So those are the things that we can discuss.